In this paper, we review variation inference algorithm for DP mixture based on stick breaking representation of underlying Dirichlet process. The Dirichlet process is measured on measures and use a non-parametric prior, and DP is parameterized by Bayes distribution Z0 and the positive scaling parameter alpha. In the Dirichlet process, we can draw a random measure G from the Dirichlet process and independently draw n random variable eta n from G distributions. The positive probability is assigned to configuration in which different eta n takes on identical values, like this. The objective of DP is that given a sample from x1 to xn from DP mixture, our goal is to compute the predictive density as following marginalization over eta. As in many hierarchical Bayesian model, the posterior p of x given a sample x through the xn is complicated and is not available in cross forms. Dirichlet process mixture model can be also defined by a random measure G distributed according to this Dirichlet process with a scaling parameter alpha and the Bayes distribution Z0 with k partitions from B1 to the BK partitions. While integrating out G distribution, the joint distribution of a collection of variable eta 1 through the eta n exhibit clustering effect because conditioning on n-1 draw, the nth value is exactly equal to one of those draws. There's the variable eta 1 to the eta n-1 randomly partitioned according which variable equal to same value with the distribution of the kth partitions. This is the number of times the value eta n r star occur in the eta 1 to the eta n-1 partitions. In the Dirichlet process mixture, as seen in these figures, the vector phi of V comprise infinite vector of mixing proportion, and the represented value set eta r star are the atoms representing the mixture component. The data can be described as arising from following process. And first, we draw independent random value Vi and eta I from beta distribution and the Z0 distribution respectively, and the assigned value of a mixture component Gn is drawn and the new data sample Xn is drawn depend on Gn and eta n r star, where the assigned value Gn is associated with the data point Xn. And DP can be simplified to stick breaking representation. The stick breaking representation of G with the two infinite collection of independent random variable Vi and eta r star is follow these equations. And the stick breaking reconstruction for the DP mixture is defined as a graphical model in these figures. Each node denotes a random variable as it denotes possible dependence, and plat denote replications. Previously, strict breaking construction for DP mixture is depicted as a graphic model. The distribution Xn, condition Zn, and the eta follow product of exponential family like this, and the association of Xn and Zn is also shown in these figures, where the A of eta n is appropriate cumulative functions. Since there is no direct way to compute the posterior distribution under DP mixture prior, variation inference provides alternative deterministic methodology for approximating likelihood and posteriors. Consider a model with a hyperparameter theta and latent variable w and observation x. This posterior distribution is latent variable is represented like this. Working directly with the posterior is typically precluded by the need to compute the normalized constant. The log marginal probability of the observation is like this, which may be difficult to compute given a latent variable become dependent. In general, MCMC algorithm circumvent this computation by constructing the approximate posteriors. Keep sampling is the simplest MCMC algorithm, which iterative sampling each latent variable condition on the previous sampled value of the other latent variables. On the other hand, the variation inference is based on reformulating the problem of the computing posterior distribution. These are based on the optimizing KL divergence with respect to so-called variational distribution. In particular, let QV of W be a family of distribution indexed by variational parameter V. We aim to minimize the KL divergence between QV of W and the posterior of the latent variable given X and mu. The minimizing in equation 11 can be cast alternatively as maximizing lower bounds on the log marginal likelihood. The gap in this bound is the divergence between QVW and the true posteriors. The variational bounds depend on parameter Vi, follow as these equations. The conditional distribution latent variable, which is represented with a member of the exponential family, where Gi is the natural parameter for Wi when conditioning on remaining latent variable, and observation X. QV of W is seen as the following family distributions. The variation bound and simplified again with P of W and Q of W as follow. In particular, the optimization of KL divergence with respect to single variable parameter Vi is achieved by the derivative with respect to Vi and computing the following equations. Repeatedly updating each parameter in turn by computing these expectations amount to performing coordinate ascent in the KL divergence. In this slide, we show the mean field variation algorithm for DP mixture. The proposed algorithm is based on stick-breaking representation of the DP mixture, and in this representation the latent variable are the stick length V and the atoms eta R star and the cluster assignment Z. Following the general recipient equation 12, we write the variation law bounds on log marginal probability of the data. V and eta R star and Z and the expectation of the V and eta R star and Z. To exploit these bounds, we must find the family of variational distribution that approximate the distribution in infinite dimension random measure Z, where the random measure is expressed in terms of infinite set V and eta R star. Here the truncated stick-breaking representation have been considered in the context of sampling-based inference for the approximation to the DP mixer model. The model is a full Dirichlet process and is not truncated, only the variation difference is truncated. The truncated level T is a variational parameter which can be fully set. We thus propose the following factorization family of the variational distribution for mean field variational inference, where the QVT is the beta distribution, Q eta R star are the exponential family distribution with the natural parameter gamma t, and QZN are the multinomial distributions. It is important to note that there is a different variational parameter for each latent variable under the variational distribution. For example, the choice of the mixture component Zn for the data point is governed by multinomial distribution indexed by variational parameter theta pi n. These reflect a conditional nature of the variational inference. In this slide, we present an explicit coordinate ascent algorithm for optimizing the bounds in equation 16 with respect to variational parameters. All the terms in bounds involve standard computation in exponential family except for the third terms. We rewrite the third term using indicator variables, and we can truncate this summation at t equal t like these equations, and digamma function denoted by pi arises from derivative of the log normalization factor in beta distributions. We now use the general expression in equation 15 to drive a mean field coordinate ascent algorithm. The update rules are defined by following equation for time t, where the st is the expectation of a latent variable. Iterating this update rule will optimize the equation 16 with respect to the variation parameter defined in the equation 17. The predictive distributions is defined by marginalization of stick-breaking representation of a latent variable. Under the factorized variation approximation to the posterior, the distribution, the atoms, and the stick lengths are decoupled, and the infinite sum is truncated. Consequently, we can approximate the predictive distribution with the product of expectation which are straightforward to compute under the variation approximations, where the Q depends implicitly on the X and alpha and gamma. For comparison to variation inference, we review the collapsed Gibbs sampler and the blocked Gibbs sampler for DP mixture. The collapsed Gibbs sampler for DP mixture with the conjugate Bayes distribution integrate out the random measure G and the distinct parameter value eta r star. The Markov chain is thus define only the latent variable C. The algorithm iteratively sample each assignment value Cn for n condition on the other cell in the partitions. The assignment Cn can be one of the assignment previous value, either the nth data point is in the cell with the other data point, or in a cell by itself. Exchangeability implies that the assignment Cn has the following multinomial distributions. The first term is a ratio of normalizing constant of the posterior distribution of the kth parameter, and the second term is given by Poilier-Ernst schemes. The approximation predictive distribution is the average of the predictive distribution across the Monte Carlo samples. As we know, in the truncated DP mixture, the state of Markov chain consists of beta distribution V and the mixture component parameter eta r star and the indicator variable Z. The block Gibbs sampler iterates between the following three steps. First, the sample indicator variable Zn and the sample stick length Vk from beta distribution, and finally it samples the mixture component parameter eta r star. After the chains has reached its stationary distribution, we collect the B samples and construct the approximation predictive distribution. Again, this distribution is average of the predictive distribution of each collected samples, and where the expectation of pi I of V given gamma is the expectation of product of independent beta distributions. These distributions only depends on Z. Other variables are needed in Gibbs sampling procedure but can be integrated out here. Figure provides the illustrated example variation inference on small problem involving 100 data point sample from two-dimensional DP mixture of Gaussian with a diagonal covariance. Each panel in the figure plots the data and the present predictive distribution given the variation inference algorithm at a given iteration. The truncate level was set to 20 as seen in the first panel. The initialization of variation parameter yields largely at distribution. After one iteration, the algorithm has found the mode of the predictive distribution, and after convergence, it has further refined those modes. Even the 20 mixture components are represented in the variation distribution. The fit approximate posterior only uses 5 of them. Left shows the optimal bounds on the log probability as a function of a truncate level, and there are 5 clusters in a simulated 20-dimensional DP mixture of Gaussian data set which was used. The light ones represent held-up probability as a function of iteration of the variation impulse for the same simulated data set. The relative change and the log probability bounds of the observation is labeled as selected iterations. Both stable as the levels and the iteration increase. To compare variation inference algorithm to Gibson sampling algorithm, we conduct a systematic set of simulation expression in which the dimensionality of data was varied from 5 to 50. Figure shows the average convergence time across the data per dimensions. With the caveat in mind regarding convergence time measurement, it appears that the variation algorithm is quite competitive with the MCMC algorithm. The variation algorithm was faster, exhibit significantly less variance as convergence time. This slide shows the comparison of a truncated Gibbs sampler and the collapsed Gibbs samplers. The collapsed Gibbs samplers converge faster than TDP Gibbs sampler. As shown in this figure, through the iteration collapse Gibbs is the slower than the iteration of a TDP Gibbs. The TDP Gibbs sampler require longer burn-in and greater lag to obtain the uncorrected samples. Table illustrates the average of log likelihood assigned to the held-out data by approximate predictive distribution. The predictive distribution based on the variation posterior assigned a smaller score as those based on sample from true posterior. Though it is based on the approximation to the posterior, the resulting predictive distributions are very accurate for this class of DP mixtures. To demonstrate the applicability of our variation approach to DP mixture in setting of a large dataset, they analyzed a collection of 5,000 images from Associated Press. On the leftmost columns is the posterior mean of each cluster, followed by the top image associated with it. These clusters capture patterns in the dataset. This figure illustrates the expected number of images associated with each component under the variation approximation to the posterior, and the right side illustrates the prior for the scaling parameter alpha as well as the approximate posterior given by fitted variational distributions. We can see that the approximate posterior is picked rather different prior, indicating that the data have proved information regarding alpha. This is conclusion of this paper. They have developed mean field variation inference algorithm for Dirichlet process mixture model and demonstrates applicability to the kinds of multivariate data for which Gibbs sampling algorithm can exhibit slow convergence. Variation inference was faster than the Gibbs sampling in their simulation, and its convergence time was independent of dimensionality for the range which they test. Both variational and MCMC method have a strength and weakness, and it's unlikely that one methodology will dominate the other in general. This is my end of my presentation. Thank you for listening.